So I just wanted to record a little video to walk you through some of the simulations that I did in class on illustrating concepts like genetic drift, simulation, natural selection, and the coalescent. So yeah, the coalescent. So this is sort of talked about on page 171 of your text. The coalescent it's actually really kind of a deep idea that there's potentially a lot of stuff to dive into, but for the purposes of this class, we're just going to treat it really cursorily. But I think running simulations can help you kind of get an idea for how things play out. I also want to make a quick little plug for um, this video that I posted on Blackboard about the concept of mitochondrial Eve and Y chromosome Adam. It's like a 10-minute video. It's pretty informative. So this concept isn't super duper crucial to understand right at this point in the course, so I just kind of brushed over it in class. But if you're interested in the idea that at some point around 2 to 300,000 years ago, all of us in this class share a common ancestor at our mitochondrial gene, and all of us and or all of your biological fathers share an ancestor for the Y chromosome. This is kind of a cool video to check out. So I encourage you to check it out. It's pretty well done, but not super duper crucial for learning for the exam. The next stuff that I'm going to show you is mostly things on an R package called learnPopGen that was created by Liam Revell. And this is a really cool R package. If you know a tiny bit of R, it's really easy to figure out. If you don't know any R, which is a statistical programming environment that lets you run stats and do lots of other fun things, don't worry about it at all. I'm just going to be typing things into a command line, and then pretty pictures are going to show up. Just look at the pictures. Don't worry about the R too much if that's not already something that you're comfortable with. So R. Yeah, let's check out R a little bit. So here I'm going to be kind of flip-flopping between R and Sublime, which is a great band from the 90s. First to load R, we load R and then we load the library learnPopGen, and then we can start doing fun things like these coalescent plots. So this is very similar to that figure that I just showed you in your textbook. See all the pretty colors? So the way you read this graph is that initially at time 0, there was heterogeneity in the population, which is represented by different colors. And then just at random, let's assume that this is an asexually reproducing organism. So it's just organisms kind of cloning themselves. Just at random, the red one in the second generation had 2 offspring, but then these 2 offspring in the third generation didn't contribute anything reproductively. The blue one over here had 3 offspring in the second generation, and in the third generation, this one had 1 offspring, this one had 1, 2, 3, 4 offspring. The purple one had 2, and then only one of them had 2. And then actually very quickly, just because of chance, really, based on how much or how little the different colored organisms reproduced, all of the organisms in the end time of the simulation, so at time step 20, can all trace their ancestry back to the blue organism. And this is essentially what's being talked about in the video when they talk about the idea of mitochondrial Eve. So you could imagine that each of these are mitochondria in people's cells. And at the time that mitochondrial Eve, quote unquote, lived, she was part of a population, and every woman and man in that population had mitochondria. But just for whatever reason, just by chance, she was lucky, and her offspring and their ancestry, or their descendants rather, ended up contributing all of the mitochondria to the present time. So obviously more than 20 time steps are involved here because it's going back about 200,000 years. But for a while, there was probably potentially times where there was more mitochondrial diversity on Earth. But just for whatever reason, now all of us are the mitochondrial descendants of this one woman who lived as part of a population, but who lived in Africa 20,000 or 200,000 years ago, rather. And same with the idea of Y chromosome Adam. Y chromosome Adam was part of a population, but just by chance, he was the father of 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 the father, dot, 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 of all of our fathers. So if we run coalescent plots, again, you see that in general, different colors win out. And it's because this process is based on just kind of a random sampling of each generation. So if you want to think about this biologically, the y-axis is the number of time steps, and each dot moving across, you can imagine that as kind of the population, and maybe this population has been at the same carrying capacity for a long time. So there's only sort of quote unquote room for 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 individuals at any one time step. And just by chance, those individuals will have different numbers of offspring, and those chance events propagate into the future to result in this situation where all of the current organisms can trace their ancestry back to just one member of the initial population. Now, sometimes if we start out with more members of the initial population, then you can potentially have heterogeneity towards the end of the simulation. So we almost got there, man. Step 29, we almost had it. But you can imagine that if we, you could imagine that if we ran this for fewer generations, like only 20, there might not be time for coalescence to happen. And so in this case, we got all the way to step 20, and there was still two separate ancestors, two separate coalescence points for this current population. So here's a coalescence point, here's a coalescence point. If we only run it for 10 generations, there's still only two. So in general, there's some randomness built into this simulation. But usually if you run it for fewer generations, there'll be more genetic heterogeneity at the end. And this is actually one of the ways that population genomicists, people who work on population genomics, so they try to infer the qualities of organismal populations based on whole genome data or samplings of whole genome data. This idea of the coalescent is one of the ways that people infer population genetic bottlenecks and effective population size based on how much heterogeneity there is now. Because if there's a lot of genetic heterogeneity in a current population, that means that either the ancestral population was always really, really big, or it was always really diverse for whatever reason. So if you see a lot of different alleles represented in the current population, that usually means that there hasn't been a super duper recent genetic bottleneck. Yeah, so n equals like 40. Generation 10 equals alternating. Yeah, so in this case, if we kind of keep what you could imagine as like the effective population size at a higher carrying capacity, then there's even more genetic diversity at later and later times. It's a little bit hard because there's only so many colors in this simulation, but here you have 1, 2, 3, 4, 5, 6, 7 separate coalescence points. Coalitions. So if we think about the coalescent for a relatively large number of organisms, but if there's only 2 color options, then you're starting to see So let's imagine that every member of the starting population within this coalescent simulation had either a blue allele or a green allele. What you can kind of do with your imagination is chart the relative abundance of blue alleles or green alleles. So even though in this simulation, not all the green alleles are coming from the exact same organism at the beginning necessarily, although by the end they might be, it's still, a population of only green or only blue. So we'll just quit that. But if we do this again, let's just do it for fewer generations. Yeah, so we're starting out with just green and blue organisms. And over time, the relative frequency goes from 50-50, green and blue, to all green. And so this idea of a coalescent plot of just two alleles is pretty much the way we classically represent the idea of genetic drift. So if instead of imagining, just one simulation where you're really keeping track of every individual, imagine one simulation where you're just keeping track of just how many blues and how many greens there are in the population. And that's the way genetic drift is usually simulated. So here, we can simulate genetic drift and selection at the same time. If you want to specify that it's genetic drift, you just have to specify that the relative fitness of each organism or of each haplotype, so like let's say big A, big A, big A, and little a is the same. And then say, okay, let's just start out at 50-50. So that's the starting frequency of the different alleles in the population. The effective population size is 100. The number of generations is 200. And let's just do one of these things for now. So this is just a simulation of the relative frequency of big A in the population through time. Time is on the x-axis. So you can see there's always some big A, always some little a, and it actually ends up not too far away from 50-50. Now it's like 60-40. If we ran the simulation 5 times, it's going to result in 5 different evolutionary trajectories, because this is just genetic drift driving the relative frequency of this allele. So there's no selective pressure. And so in this case, every simulation has a slightly different trajectory. And in fact, this blue simulation shows that at the end of the simulation, allele big A was driven to fixation, and there was no more little a. And in the green simulation, the little a allele was driven to fixation, and there was no more big A. And then purple, whatever this is, chartreuse, and red, these all show that there is still some big A and some little a in the end of the simulation. What you'll notice is that if you change the effective population size to like 500, the simulation takes a lot longer to run. But there's more likely that you're going to end up with both alleles represented, because genetic drift does not act as quickly in populations with larger effective population sizes. So in the end of the simulation, after 200 generations, you still have both alleles present in every simulation. If we wanted to do like 10 simulations, that also takes longer. This is still showing that there's, in 10 separate simulations, you see 10 different genetic drift trajectories, but they all end up with some proportion of big A, little a. If you change the effective population size down to 50, then you're much more likely to observe fixation. And so in this case, only 2 out of 10 didn't go to fixation after 200 generations. If we increase the number of simulations to 20, you can see that it's still a relatively modest number that don't go to fixation. So 1, 2, 3, 4, 5 out of 20. So only a quarter of them don't go to fixation. If we have the effective population size at 20, everything goes to fixation. 20 for 20. Now, if we start introducing differential fitness for the different haplotypes, we'll start to see more repeatable evolutionary trajectories in these different simulations. So in this case, it looks like it's close to 50-50 on which allele went to fixation. But if we introduce differential survival and reproduction that is non-random with respect to the genotype, so let's say we make this 0.8, so it has a lower relative fitness, and this 0.5, so it has an even lower relative fitness. Everything very quickly goes to fixation for big A. If we switch it around, if little a is better, 0.5, this one's 0.9, everything goes to fixation for little a, right? That's pretty obvious. So one of the interesting things that comes into play, which is of interest to you if you're a conservation biology major or a wildlife science major, is that even if one of the alleles is deleterious, if you have a really low effective population size, you can still sometimes have fixation for the wrong allele. So in this case, we actually didn't see fixation for the wrong allele. But as you move the... Wow, that's cool. Oh, that's 80, right? That's not 8. So as you move the effective population size down, you sometimes run the risk of having a fixation of a deleterious allele. You have an effective population size of like 5. Still only 1 out of 20, but that's not great. The way natural selection usually works is that you're not starting out at a 50-50 frequency for an adaptive allele. Adaptive alleles enter the population at relatively low frequencies. So let's say the frequency of big A at time 1 is 0.01, so that means 1 out of every 100, and there's an effective population size of only 100. So let's bump that up a little bit, and then we'll make big A adaptive again. 0.4. What you'll see is you'll still have the fixation of this allele, even if it's starting out at very low proportions of the population. As the starting proportion of the population gets lower, then you might sometimes see the loss of this potentially adaptive allele. So if it's 0.1, we might see it go to fixation the wrong way. Oh no, everything's cool. Sweet. Awesome. If the selective differentials are similar to each other, so let's say this is 0.55, this is 0.5, and this is 0.45, then it's a little bit more kind of hit or miss, and it takes longer for the allele to reach fixation because the difference in survivability and or reproduction that's conferred by having that allele is a much smaller difference. So big A is still better than little a, but it's not that much better. So if the difference in the relative fitness is only like 0.55 versus 0.45, and then the heterozygotes are 0.5, you see very different evolutionary trajectories than if they're higher. Yeah. So this one, fixation is reached more quickly, but you do still have a couple of puppies that are down here with the deleterious allele. So you run into some cool things sometimes. So let's say we're starting with 0.3. Let's say we're starting with, okay, 10. Effective population size is 100. Now, what if the heterozygotes have an advantage? What does that look like? So the cool thing about overdominance, or a heterozygote advantage, so when big A is better than either big A or little a, then you can actually have the maintained condition in the population where you have both alleles. So because heterozygotes are at an advantage, they drive the persistence of this genetic diversity in the population. So big A and little a stay at sort of a constant equilibrium. I mean, there's a lot of squiggle here, but this represents, what I think a lot of population geneticists would refer to as an equilibrium state. And so overdominance is one of the ways that you can observe genomic diversity or genetic diversity in a population. So that's one of the ways that polymorphisms persist in a population, is overdominance. Let's start this out a little bit higher. What if both of the homozygous conditions are better than the heterozygote? Then usually what happens is one of them will go to fixation. But interestingly, it often depends on what the starting frequency of the allele is. So in this case, if there's underdominance, if there's a heterozygote disadvantage, and both homozygous conditions are adaptive with respect to the heterozygous condition, then you'll see fixation of whichever allele started out at a higher frequency in this population. So if you start them out at 50-50, you have different alleles going to fixation. And if you started out pretty close to 50-50, you usually don't. But if you decrease the effective population size, then you do. So you have different alleles going to fixation if you decrease the effective population size, which is kind of cool. So underdominance is actually sort of a way that polymorphisms can persist within a species if it has a pretty big range and a lot of little subpopulations. So imagine that each of these simulations represents a subpopulation. Whatever the starting allele frequency in that subpopulation is will drive the fixation of one allele or the other in the case of underdominance. And sometimes this is potentially a mechanism for speciation too. So underdominance, if there's a heterozygous disadvantage, that can drive the adaptive divergence of two different species. So ecological speciation might occur if there's a situation like this. We'll talk about that after the first exam. We'll talk about speciation later. So I think that's pretty much all I wanted to say. Definitely let me know if you have any questions, and I hope this was helpful. Okay, bye.